Mm. Is it visible, the screen?
No, hello.
Not yet.
Okay, okay. Okay, I forgot to share it. Okay, just a minute. Mm. Okay, I think now it's visible.
Yes, visible.
Yes, it is visible now.
Yeah. Okay, just we'll quickly revise some things. Um, Fine. So let's have a quick revision on continuous random variables. Okay. CRV or continuous random variables. Um, okay. So basically, okay. So um, so the density function of continuous random variables looks like this. Okay. Now the thing is, the continuous random variables, they can, as I mentioned earlier, they can take values in continuous intervals, right? So the thing is, how am I supposed to compute probability of a certain event? Okay. So what happens actually in case of continuous random variable, let's say this is your event space, okay? Let's say this is your sample space omega. Okay. It's continuous in nature. Now, let's say I'm interested in finding probability of this particular event. Okay. This particular event, let's say this event is denoted as set B. Okay, which is a subset of omega. I'm interested to find probability of this particular subset. Now, if I is okay, so this is all happening in the event space. Okay, this is all happening in the omega. Now I want to see it in terms of a graphical representation of probability density function. Okay, so what happens? Whatever event is present in the omega. Okay, whatever set of events are present, they actually map to a portion of a real line, like as I earlier said, that a random variable x is nothing but a function from your sample space to real line, right? So this particular event, it will be get mapped to a particular portion of real line. Okay, this it is getting mapped by a random variable x. Okay, and now so what basically what is the probability of this area? Okay, so the probability of this area is basically given by this. You have any doubt in this particular formula?
No, sir.
Okay, so it's basically the total number of possible events by the favorable events, right? And here the probability is given by this, the area. So this is a set. This set is being mapped to a particular real line, and within the real line, into this particular portion, I am supposed to find the area that is covered by the PDF. Okay, the area that is enclosed by the PDF. This thing. Okay, so it will be A to B. So I can clearly say that probability. Oh, by the way, when I compute, when I say this, when I say uh, probability of a set in omega, okay, you can write it as like this: probability x belong to that set, random variable belongs to that set. Okay, it is written like this. Okay, so here the probability that a random variable x belongs to the set B, let we name it by set B. It is nothing but equal to integral of yeah, this is it. This is B, integral of um, A to B fx dx. Okay. Now, are we clear till now? Like you got a notion like how you compute the probability of how the probability of a particular set in a sample space maps to the area of a distribution of a continuous random variable. So does it make sense? Like you got it?
Yes.
Okay. Now, okay, this is fine. And basically, when I say this thing, okay, um, this thing, it's basically, it's not this particular, this represents cardinality of a set, right? So if I have a discrete set, B, let's say B1, B2, dot dot BK, okay, so it will be equal to K, right? It is the cardinality of set. But here the space is continuous. The space here is continuous in nature. So basically, I am not supposed to use this thing, this cardinality. Rather, I will use something known as measure. So basically, I am finding a measure or a tool, okay, which can measure the set B. Okay. So if I say that I have this particular thing over here and this is the set B and I'm interested to find the probability of the set B, okay? And let's say that I am not provided with any probability density function. So what I will do, I will define some measure. Let's say M is a measure, M of B by M of omega. So this will be the probability. Probability of B. Now, can you, okay, if you can see the image clearly here, let's say this circle, okay. Let's say this circle is omega, and let's say this small circle within it, it's B, okay, it's a set B. Now, can you like vaguely think of some measure M? Like in this case, what can be a like good measure? Can you think of any measure?
area enclosing B.
Yeah,
Uh,
yeah,
uh,
that can one of the measure. So area enclosing the B by area of omega. Okay, and here you can define certain other measures also, but we won't go in depth to that because that's a totally different branch of probability. Okay, so we will stick to just it's just to make you understand like how the stuffs work here. Okay, and another thing, and now I will give you a definition of PDF. Okay, so I will give you a definition of PDF, the probability density function. Or not a definition, but I will give you significance of PDF. Definition, we all know that a function f is a PDF if it satisfies two property, non-negativity and area under the curve is 1, right? So we will just give you a notion of PDF. Brief notion of PDF, like what PDF actually is. So let's say I have this graph with me. Okay, so this is a PDF, fxx. There's a nice PDF over here. Now what I want you to choose a small area, okay? A very small area. Let's say this point is x and this point is x plus dx, okay? And I want to find the probability of this area, okay? So I want to find the probability of this area. Okay. Now, can you tell me what this integral will become? Okay, for simplicity, let's just write this. Let's just write it as delta x. Okay.
It will be fx into dx.
Exactly. Fx into delta x. Yeah, right. Um, because this particular area, na, if you can see, it can be approximated as a rectangle, right? The length of the rectangle is fx. This length is basically fx, and the width is what? The width is delta x. So it can be approximated as fx dot delta x. Or clearly I can write that probability a random variable lies in a small area is nothing but delta x, or I can write you know what this formula shows, what this formula signifies. The formula says that I have a PDF which is approximated as some probability. Okay, so this thing is probability, right? This thing is probability. And what is dx, delta x in this curve? It's sort of length, right? Uh, you got it? I can say now that this particular dx here is a length. And this thing is a probability, right? This thing is a probability, and this thing here is a length in a real number line. So basically, when you, the main idea behind PDF is nothing that a PDF is basically defined as probability per unit length. Okay. The PDF will never give you an idea about the probability, but it will give you an idea about what is the probability per unit length. Okay. Or per unit space. Okay. So it's basically a quantity. Am I clear on this, or there is something
Uh,
that I need?
yes.
Okay. Yeah, so this is the basic like notion on the probability density functions. Okay. And yeah, again, I will uh, uh, I have a brief overview on this. Basically, if I have a random variable x, okay, then its mean is denoted by mu, which can be written as integral plus infinity to minus infinity x times of fx. Fx is the PDF of x, okay? Or it can be written as expectation of x. Okay. Now, expectation of any function gx of a random variable, it can be written as again minus infinity to plus infinity. It will be gx fx dx. Okay. And the variance sigma square, it's nothing but minus infinity to plus infinity integral x minus e of x whole square fx dx. Okay, or it can be written as expectation of x square minus expectation of x whole square. So these three things, 1, 2, 3 for any general continuous random variable. Okay. Now, okay. Let me give you a simple question. X is a continuous random variable. Okay, with a PDF of fx, and the PDF fx is denoted by is equal to k kx for x in 0 to 1 and 0 else. Okay. Now, can anyone tell me where this k is a real number basically, yeah? Now, can anyone tell me what can be the value of k? Hmm? You got the question, or shall I need to repeat it again?
Is it 1 by x? No, it's a constant, right?
Yeah, k is a constant. So what can be the value of k? What will be the value? Can you please mute yourself? It's yeah. No, I'm asking about the value of k. It cannot be 1 by k, right? What will be the value of k? Uh, there's a lot of noise coming from someone's background. So.
So, if you look at it, f of x is a probability density function. It should have
Yeah.
the dimension of 1 by length. Probability density function is a number.
Probability density function is a probability per length. It's basically a function, right? Probability density function is a function. I am asking that, okay, I am given a PDF which is defined as k into x, okay, when in the range 0 to 1 and 0 elsewhere, and k is a constant. Now, if I say that fx is a probability density function, can you find the value of k?
Yeah, that's what I'm trying to say. If you look at fx is represents a probability density function, it should have 1 over length as the dimension. So k should have 1 over length square because x is taken a length. So it should have something
Mm,
divided by length square.
no. See, it was pretty simple. Like, okay, so first, yeah, tell me what were the two properties that a PDF should satisfy? What were the two properties that a probability density function should satisfy? Am I audible? Hello, am I audible?
Yeah, you are audible.
So the first property is fx should be greater than or equal to 0. And the second property is, actually someone has said k equal to 1. Or k equal to 2, I think. Yeah, so that will be the correct one. And the second one. So I think this particular property can help us. If I claim that fx is a continuous random variable, it's written already here. So it should satisfy this property. So using this property, minus infinity to plus infinity, k times of x dx. If I split it, it will be 0 to 1 kx dx, right? And the other part, they will vanish because elsewhere it's 0. So it will be k dot x square by 2, 0 to 1 equal to 1. And it will be equal to 2. Got it? Any doubt in this question?
No, it's okay.
Yeah. Okay, equal to 2 in this. Okay. So, yeah, that's how you compute the probability. And let's jump to something known as CDF, or the cumulative density function. So a function is cumulative density function. It's denoted by capital F, random variable x of small x, and it's defined like this: probability of, okay, this can be written as integral So any doubt in understanding this formula? Yeah, so it's a pretty simple formula, right? Um, so, okay, now let me give you a PDF, just simple PDF. A to B. Can you, if I am given this particular PDF with me, this PDF, can you tell me what can be the CDF, how the CDF will look?
You have to compute all the probabilities for all x's less than equal to x and add up the probabilities.
Yeah, that's what the CDF means. Yeah, exactly. So let me tell you. Okay, so let's try it. Okay.
So for
Not exactly trying.
continuous random variable, you need a function, right?
Yeah, CDF will be a function for continuous as well as for discrete. Okay. So we know that the cumulative density function is nothing but this, right? So let's assume that my x lies from 0 to a. Okay, let's assume that the x lies from 0 to a. What will be the CDF then? If my x lies between 0 to a, what will be the CDF? Yeah, it will be 0, right? See,
It will be 0.
yeah, so probability cumulative density function, it's basically probability of a random variable less than equal to x, and you have to take all possible cases where your x can lie. So for 0 to a, the CDF will be 0. Now the second case, what will be the CDF? Oh, this, yeah. No, you have to give me a function. You cannot say it's a sort type.
You have to give
Okay,
the value there. You have to give the value there. That multiplied by b minus a.
pardon, come again?
So this value is there, right? this value of the sawtooth function.
The way, if I say that this is a PDF A to B, yeah, then you should have first asked like what is the amplitude of this? What can
Yeah,
be this value? What can be this value?
that is 1 by b minus a.
Yeah, exactly. Should be 1 by B minus A because I want the area to be 1. Yeah. Now, if I say that my x lies here, so it will be integral A to x, right? It will be integral A to x. It will be integral A to x. Mm. Can you please mute? Like there is a lot of background sound coming. Yeah. So the 1 minus b to a, it's a. So 1 minus 1 by b minus a, it will be a constant, it will go out, and we will be left with only integral a to x, right? Dx. Okay. What it will be? B minus a, right? It will be b minus a. So it's basically a linear curve, right? It's linear. Now, what will be the PDF for x greater than equal to b? A CDF. What will be the CDF for x greater than equal to b?
0.
No, no, no.
1. It should be 1.
Yeah, exactly. It should be 1, right? If you can, so it's basically what it's happening. At every x, I am computing the area behind it, right? So if x is lies between 0 to a, the area behind it will be 0. If x lies between a to b, the area behind it will be this thing, na? This particular area, right? So rather than doing the integration, we could have directly computed this. So length into breadth, right? So it was x minus a was breadth and the length was 1 by b minus a. And where x is here, I am just supposed to compute whatever the area is behind x, right? Whatever the area is behind x. So if my x is here, I will be computing this whole portion of area. I will be computing this whole portion of area, right? This whole area. This whole area I will be computing. So this whole area will be, it will be 1. Now, if I can plot this as the CDF, it will look something like this, right? The CDF will look something like this. The Yeah. So initially the CDF will be 0, 0, but as soon as the x goes in between a to b, it will start climbing as linear thing. As soon as x goes beyond the b, it will saturate to 1, right? So here is 1. So here, this is how the CDF will look like. Okay. Any doubt in this?
No, sir.
Okay. Yeah. And okay, so I will ask you some quick properties. Just let me know what will be this. Yeah, it will be 0. Exactly. What will be this? No, this is not 0. It's fx of infinity. Just compute it. Try to compute. Okay. Let me give you an example. Assume this is a PDF, okay? Like this is a PDF, okay? Let's think that this is a PDF. Now, fx of minus infinity. Fx of minus infinity means probability that your x is less than equal to minus infinity. So here this particular PDF lies from minus infinity to plus infinity. So probability of x less than minus infinity, it means the x particular thing, it should lie somewhere here, like deep down to minus infinity, right? And you can see for any PDF, okay, for any of the probability density function, the probability of x less than minus infinity, it means you are going very far beyond of minus infinity, it will automatically be 0, because there is no, at minus infinity there is no, what you say, amplitude or peak of the density function, right? But if you ask about this, fx is equal to this, okay, fx equal to fx of infinity, it will be probability of x less than equal to infinity. It means probability of x less than equal to, yeah, so probability of x less than equal to infinity, it means you take some point x at infinity and then you start computing the area behind that point. That's what the CDF is, right? You compute the area behind the point. So x less than infinity, it will be 1, because we are computing all the area. So it will be 1. So far, any doubt in this?
No.
Okay. Now we will just talk about some, what do you say, some property of expectations. So we'll talk about some properties of expectation and variance as well. Okay. So the properties, it will be, okay, so x is a random variable. So x is a random variable. Now let a comma b be some real number, okay? First thing, the property is expectation of can you tell me what it can be, expectation of ax plus b for any continuous random variable? So it will be basically a times of b. Can anyone tell me how it came, or shall I derive it? Okay, I will just quickly go and derive. You have to start with the basic formula. Okay. If I have to split the integration, it will be ax dot fx dx plus integral dx, right? Now as a is constant, b is also constant. This will be what? This will be x of x, expectation of x, right? So it will be a times of expectation of x plus what will be this integral?
1.
Yeah, this integral will become 1. So it will be b. Hence, expectation of ax plus b is nothing but a times of expectation of x plus b. So this is known as linearity property. Okay. This is linearity. And the second property. To second property. Let's talk about variance. Okay, let's talk about variance. So variance, let's say that sigma, sigma square equal to variance of x. Okay. Now can anybody tell me what can be variance of ax?
A into variance of x.
Let's solve it. Okay. So it will be integral of, yeah, it will be a square variance of x. So it will be integral of this will be a square times of variance of x. It will be okay. So let's prove it. So variance of x can be written as x minus mean mu whole square fx dx. So variance of ax can be written as integral of ax minus ax minus a mu whole square fx dx. See, there was ax, hence ax is here. Now mu is nothing but expectation of x, right? So the expectation of ax will be what? Expectation of ax will be a times of expectation of x. So that's why a of mu I am written here. So basically I'm denoting mu as expectation of x, okay, here. Now you can definitely take a square out and you will get this. Hence this will be a square times of.
Will we not get fx of ax here?
Effect of ax means
Here, fx of ax. because you are taking variance of AX.
Yeah, so variance of AX is a random variable. Okay, let's denote it as random variable y equal to small ax. So this integral will become something like y minus expectation of y whole square. Okay, let's not put here. I have to. Yeah. Um. No, we are taking the variance of ax, right? That's why I've written ax over here. Okay, this is my whole variable. And here, when I take the variance of x, I'm supposed to write the mean of that random variable in the argument, right? Here it is x, hence the mean is mu. But here it is ax, hence the mean is a mu. Okay.
Yeah.
Now
But what
the
about
random,
fx of AX?
yeah.
Here you
So
should get AX, right?
no, the random variable is x here, right? So the density of the random variable goes here, right? Because see, when we are doing expectation of g of capital X, it is basically what expectation of g of capital S is integral of gx dot fx dx. So whatever random variable is inside, only its PDF goes here.
Okay,
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 yeah. And this
okay.
law basically it's known as something. It's actually a good observation. It happens, like when I was also doing probability in the beginning, it happened with me. But you can actually see something in internet known as law of there is a noise coming from someone's background. Law of unconscious statistician. Law of unconscious statistician. You can look ahead, and you can look it in internet. You will get the brief idea why this happens. Okay. So in order to understand this thing in more depth, you are supposed to look at the law of unconscious statistician. Okay. Now, can anyone tell me what will be the variance of ax plus b? Anyone? Yeah, it will be same. It will be same. In order to see yourself, you go there, compute the variance, do the integration, and you will be able to get the answer. Okay, it will be the same basically, and it makes like sense. The reason being, let's say, I have this particular PDF with me. Okay, let's say I have this PDF. Okay, now this is a PDF of random variable x, and let's say I give you a another PDF of ax. Okay, let's say I scale it with a. Okay, so when I scale it, it becomes like this. So if its variance is sigma square, it will be definitely a square sigma square. But if I shift it, okay, so if I shift it, so variance basically denotes what? It denotes the spread, right? Variance basically denotes the spread of your distribution, okay? So if I multiply my random variable with some constant, the spread will change. But if I add something, it will just shift from this point to this point. Okay, it will just keep on shift. It will just keep shifting. So the spread won't get affected when you add something. Okay, so when you add something in a random variable, the spread will remain constant. But when you multiply something in random variable, the spread will change, and that's the reason why the variance of ax plus b is similar as variance of ax. Okay, because when you shift the distribution, the spread won't change, and variance denotes the spread. Yeah, but if you multiply the distribution with something, the spread will change. So this is the main reason why the variance of ax plus b is equal to variance of ax. Okay. Okay, I think we have covered pretty new things. Okay, I will go then to the discrete things. Yeah, tell me what doubt you have. Yeah, Bhavya, you are saying you have some doubt. Just tell me what is the doubt. What is precision? Basically, the precision is defined as 1 by variance. Like in statistics, when you tag the term precision, it's defined as 1 by variance. Okay, cool. I think we will just um, go to the probability mass function. Just a minute. Give me a minute. Yes. So probability mass functions. They are not actually as hard, but probability mass functions, they can be confusing at some time. Okay. So I have defined something earlier. Probability mass functions, they are defined only for discrete random variables, right? So here is example of discrete random variables. It can take a number of values, and for every value you can assign some probability, right? Like tossing of like rolling of a die, it will be 0, 1, 2, 4, 5, 6, right? So these, wow. So these things are basically x1, x2, x3, x4, x6, and associated with each you have certain probability. So these all are 1 by 6, right? So if I plot the PMF of this experiment, how it will look?
Bar graph.
Yeah, it will be a simple direct delta, 1 by 6, right? All. Now, tell me one thing. If for this experiment, 1, 2, 3, 4, 5, 6, right? Oops, oh, it will be 1. Sorry, it will start from 1, my mistake. Yeah. Now, can anyone compute the CDF of this? Can anyone think how the CDF will look?
Stepwise graph.
Yeah, it will look somewhat like stepwise, because see, if my x is here, okay, let's plot the CDF side by side. If my x is between this thing, it will be 0, right? Once I get my x here, the area what it will be? It will be 1 by 6, right? So it will rise to 1 by 6. Now if I get here, if my x is between 2 to 3, what will be the area? 1 by 6 plus 1 by 6? It will be 2 by 6, right? So if for x equal to 1 and for x equal to 2, it will be 2 by 6, right? 2 by 6. If my x is here, it will be 3 by 6 because I'm adding all the things which is past me. Okay, so the density will remain constant 2 by 6 till 3. Once it's encountered the 3, it will become 3 by 6 and so on. It will get saturated to what? It will get saturated to 1. Once I get here, the density will be 1. So it will have something like staircase function. So for discrete random variables, the CDF will always be a staircase function. It's always be a stairwise function. Okay. Now, are you clear in this or shall I need to explain it again?
Clear, sir.
Yeah. So this was the main takeaway thing from the CDF basically. And I think I am supposed to talk about probability models. So let's see, we have still half an hour, right? Okay. In that half an hour, yeah, let me give you a brief diagram of how discrete random variable works. Okay. So okay, let's find the notion. Okay. Um, let's say this is a discrete sample space and these are the sample points. Okay. Now in this sample space omega, these sample points are basically denoted using this thing omega i's. Okay. So like omega 1, let omega 1 be hh, let omega 2 be ht, omega 3 be th, omega 4 be tt. Okay. So you denote the elements of the sample space as omega I. Okay. And yeah, and when you apply a random variable x on there, let's say number of heads, so it will plot in a real line, okay, in 0 1 2. Okay. So if I want to define something, let's say probability of x equal to, let's say I want to define probability of x equal to 1. So I have to write it like this: probability of all omega lies in capital Omega such that x of omega is equal to 1. It means that when I say that probability of x equal to 1, so what it means? So probability of x equal to 1, right? It will be some direct delta, but how you computed the probability of x equal to 1? One head, it will consist of these 2 points, right? So basically the random variable x has mapped these 2 points here, right? At x equal to 1. So if I say what is the probability of x equal to 1, it means probability of all such points in omega where your x actually can take equal to 1 value. Okay, so it's probability of all of the point omega belongs to omega such that x of omega is equal to 1. So what will be this set? The set will be right. And what will be the probability? Did you understand?
Yes.
Yes, yes.
Yeah. So basically, x was the random variable that mapped these 2 points to 1. So if I talk what is the probability of x equal to 1, I have to look back to the omega set and find those omegas for which x equal to 1 was responsible. So I found these two omegas, okay? So when I say x equal to 1, it means head comma tail is one possibility and tail comma head is another possibility. So the total possibility will be the addition of these two probabilities, that is 1 by 4 plus 1 by 4, which is nothing but 1 by 2. Okay. So this is how you deal in discrete space. And let's talk about some famous discrete models. Okay. Mm. Now let's say I define something, a random variable x as, uh, let me define the random variable x as number of number of tosses until first head appears. Okay. So the random variable x, basically, let's say I am tossing my coin and I want to note down what is the number of tosses that happened before my first head occurred. Okay. And let me denote something like the probability of head is, let's say, denoted by p, and the probability of tail is denoted by 1 minus probability of head, which is nothing but 1 minus p. Okay. Now, if I ask you the probability of random variable x equal to k, when I say that probability of random variable x equal to k, I'm basically asking what is the probability that the first head appeared after k number of tosses. And every toss is independent. Okay, so can anyone tell me what will be the formula? Like what is the probability of first head happening after the kth toss? See, x is a random variable that denotes the number of tosses until the first head. So I am asking you to find the probability of x equal to k, or the probability of the first head appeared after, or sorry, the first head appeared.
1 minus p to the power k minus 1 into
Yeah, first head appeared on kth toss. So it will be 1 minus p. It means I got tail on the first toss. I again got tail on the second toss, dot dot. I got my tail on the k minus 1th toss. But at kth toss, I got my head. That is the probability p. So it will be okay. So you can,
Can you explain this once again?
yeah. So it's basically I'm saying x denotes the number of coin tosses until the first head. Okay. So basically x denotes the number of tosses that are required to get the first head. So if I say x equal to k, it means I am saying that my first head has occurred on the kth toss. Okay. So if I say that my first head has occurred on the kth toss, it means on k minus 1 toss, I was getting tail. All the tails were there, right? So in first toss,
Yes.
I got a tail, that's probability 1 minus p. On second toss, I got another tail, that's probability 1 minus p. On k minus toss, also I got another tail, that is 1 minus p. But on kth toss, I got a head, that is probability p. Hence this formula is here. You have to multiply all the things.
Okay.
So this model, probability of x equal to k equal to 1 minus p k minus 1 p for all k belongs to 1 comma 2 comma 3 comma dot dot dot. This is known as geometric random variable. Okay. If my x has a probability mass function something like this, then I called x as a geometric random variable. Okay. So this was the first thing. Geometric random variable. Okay, and where p is basically the probability of success. It's basically the probability of success. Okay. Now, let's talk about something, binomial BMF. Okay.
So when you tell probability of success, you mean that the number of times you get a head over the total number of times you toss.
P, yeah, exactly. That's it. If I define probability of success as probability of head, it will be 1 by 2. Okay, binomial PMF.
So means we are in this 1/2 unbiased.
Pardon?
Like unbiased, if the coin is unbiased, then only 1/2, right? I mean, okay, it's a trivial.
Can you type? There is too much of noise when you are like. Okay, I think I will. Okay, yeah, sure. Mm, okay, I think I. It's already 8:40. We still have 20 minutes left. Maybe I can quickly discuss about joint density. I think once I discuss about joint density, then we can, like, as the course will progress, I will, whenever there is a need to define any probability model, I will define it on the spot. But before that, I will define something known as joint density. Okay. Um, so joint density, just okay, joint BMFs. Just a minute. Yeah. So we'll just quickly define about joint density. Okay. Let's say now I have two random variables with me, x comma y tuples. Okay. And let's say that x is a random variable rolling a die, and y is another random variable rolling another die. Okay. So x will take values from 0 to 6. Similarly, y will take also values from, 1 to 6. X will take values and y will also take values from 1 to 6. Okay. Now, if I ask you, can you tell me what is the probability? Okay, and I'm rolling these two dice at once. Okay, I'm holding these two dice and I'm rolling them at once. Now, can you tell me what will be the probability of x equal to 2 and y equal to 2?
1/36.
Like if I, yeah, it will be exactly, it will be 1 by 36.
Uh, One more thing, when you told you are rolling simultaneously, does that mean to avoid that conditional probability confusion? I mean,
No. There is
Then
no term of conditional probability. No, there is just independently I am rolling them.
okay, mutually exclusive events like just
Exactly,
if.
exactly. Exclusive. No. Yeah, so it's basically I am rolling these two dice simultaneously, and that's the very plain notion. Okay, so there is nothing conditional thing that's happening. There is no dependence. There, these are two independent tosses. So whatever value that it will get. ah, Okay, so these are two independent tosses. Now you can what you can do, you can like take the sample space as like this. Okay, like this is X, this is Y, and you can say this is 5, 6, and here you can say what is the probability when x equal to 1, y equal to 1, what is the probability when x equal to 2, y equal to 1, like this. So total in this particular, when you define something jointly, okay, I'm talking about a joint distribution here. So total there will be how many? 36 points, right? Matlab 36 possible outcomes will be there, right? So my sample space, it has basically 36 points. So it's basically the Cartesian product of these two sets, X and Y, right? This is the Cartesian product now. And on top of that, in the 3D view, it's just like comb, okay? Like these impulses will be there, just like a comb. These impulses will be out there. 1 by 36, 1 by 36, 1 by 36. Okay. And this thing is known as the joint distribution. It's denoted by P of X comma Y, jointly defining two random variable. So it's basically joint PMF. Okay. Any doubt in this example?
Here, the events are mutually exclusive, right?
Events of rolling one die is mutually exclusive, but when you are rolling two dice, they are independent in nature. They can take any value they wish.
Okay.
Yeah, they can take any value they wish. Okay.
So there is no dependence on one on the other.
No dependence. Whenever I'm talking about X and Y, these two are independent in nature. Okay.
Okay.
These two are independent. Independent tossing of two die. Two dice. Okay, these are independent events. I think it's 15 minutes still remaining, but I think I need to go and I need to catch up with few things. So we'll be ending today's lecture here with a basic definition of what is known as joint PMF. Or before going that, I will explain you another thing. I will just give you a brief idea about what is a joint PDF, probability density function. Okay. Now, for a Gaussian distribution, a single random variable, it looks like this. Okay, where x is your random variable. Now, if I say I have a random vector x, okay, which consists of two random variable x1 and x2. So it's so here it was basically one-dimensional Gaussian, right? It was one-dimensional Gaussian. I will visualize how the two-dimensional Gaussian looks like. Okay, so this random vector x is a 2D Gaussian. Let me tell you, it's a 2D Gaussian. So it looks like this, okay? So I have my x1 random variable here, I have my x2 random variable here, and I have a probability density function denoted by x1, x2, x1, x2. Okay, so it will look something like this. So now rather than having a one-dimensional case, I have something known as so this thing is your sample space, which is basically an R2 plane or some subset of R2 plane. Let's say it's denoted by B, it is some subset of R2 plane. And on top of the plane, you have the density. In one-dimensional case, you have a real line, and on top of line, you have density. But in two-dimensional case, you have a R2 plane, and on top of that, you have a density. Okay. So in visualization term, this is how the what do you say? This is how the joint PDF looks like, the probability density function of joint random variable. Okay. So any doubt in this joint thing?
No, sir.
And in the two-dimensional case, we have denoted x as x1 and x2, but we will generalize this thing, okay, for n random variables. So let's say x is a random variable of n random variables. So it will consist of n number of random variables, okay? And now in 2D, I can visualize using graph, but in n dimension, I cannot visualize using a graph because I cannot visualize more than 3 dimensions, okay? So it's just a general extension of n dimensional random variable, okay? And most probably we'll be dealing with n dimensional random variables in upcoming machine learning thing. So I think from next lecture, we can directly start machine learning. I just have to give you a quick overview of 2 or 3 things, and then we will directly jump to the machine learning, the classical concept. So the next lecture, we will discuss something known as ML estimate. Okay. And we will talk something about KL divergence. Okay. First, we will talk about KL divergence, and then we will jump to ML estimate. Okay, in next lecture. And before that, I will be sharing 2 YouTube links. So there is my batchmate Piyush Tiwari. He is also doing PhD in same signal processing and machine learning. So just like me, he is also TAing for his PMRF thing. So he has actually I'm teaching the machine learning, so I'm unable to teach you whole of the probability. But he is taking a full-fledged course on probability, I think, and it will be a 1.5 hour lecture. So there will be 2 lectures of 1.5 hour. I will be sharing the YouTube's link just after the lecture ends in the Discord group. You can go through that and you will have a very good understanding of the probabilistic things. Okay.
Okay, Alok. And Alok, what about your lecture, yesterday lecture?
I am uploading them on YouTube, so I will share you the YouTube link. Okay.
Okay. Thank you,
And
Which
Alok.
this
books?
Yeah.
recording also, sir. This recording
Yeah,
also.
yeah. This will also be there.
Which book
Okay.
should be will you be referring for ML estimate and KL divergence?
I haven't read some books like this, so it's basically whatever I have read from research papers or my professor has taught, I will be teaching that.
Or which book should we refer?
Basically, for books, you can refer this book that I usually found very useful. And, so,
Christopher Bishop.
no, Christopher Bishop is good for deep learning, not for machine learning. So the book,
Okay.
can you please mute? There is a sound. Yeah, so the book's name is Pattern Classification by, there are 2 authors, Duda and Hart. So this book is a full-fledged book on machine learning for ML. Refer to this book, Pattern Classification by authors Duda and Hart. Okay. And mostly whatever I will be teaching here, I will take the reference from that book only. Okay.
Okay.
So